Tried using a splint, didn't work, made it worse.
Should I write you?
No, like it actually hurt worse with the splint on. If I just leave my hand in front of you, it doesn't hurt. But the splint was just rubbing up against it and like digging into it. It's like, no.
I think JC put it
Alright, so this lesson is just kind of a reinforcement and a tiny bit of new material, but more of a reinforcement of what we talked about on Friday. Okay, when we started talking about where a derivative might not exist. Alright, so it might be a good idea to take some notes here. Notes are blasphemy. Alright, so
Hey, we're trying to learn.
Keyword is trying.
try. Yes. Okay, so we can say that a function might not have a derivative at a certain point. Okay, a f of a is just another way of writing x, y, where the slope of the secant line. So what is a secant line?
Oh, wait, okay. Opposite. It crosses twice.
Right.
Good job, bud.
A secant line, okay, is a line that hits a curve in two places. It crosses it twice, right? What we've been working with are tangent lines, right, that only hit the curve at one point. But we said a secant line hits the curve at 2 points. Right? So this, f of x minus f of a over x minus a, or y2 minus y1 over x2 minus x1, right? That's just slope of a line. So if we're talking about a secant line, that's a curve or a line that hits the curve in 2 places. So the whole idea of what we've been defining a tangent line to be is saying, well, we want to make these points get closer and closer together until they're the same point. Okay, that's the limit as x approaches a. So what we have defined the slope of a tangent line to be was this. Right? This is the one that we've been working with. This is just another way of writing that. Okay, so I can say the limit as x approaches a of f of x minus f of a over x minus a. These are just 2 different ways to define the same thing. Okay, this is the one we have been using. This is an alternate version. Right, so we're just saying we've got 2 points, right, to define the slope of a line, and I'm just making them go closer and closer together until they are actually the same point. That's how we're defining a tangent slope. Right, so this definition is a little bit easier to think about where a tangent may fail to exist. All right, and we started talking about this on Friday. Right? The first one was a corner. Right? If I think about, let's say I've got this point right here, that's my f of a, that's the point where I want to find the slope. And I say, well, I'm going to take a point over here, and I'm just going to make it closer and closer and closer until I get that same slope, until it's that same point. Right? Well, if I try to draw that tangent line, it would be this line, right? Well, what if I do the same thing from the other side? What if I choose a point over here and just start getting closer and closer and closer? Well, that would be, if I drew the tangent line, it would be right there then. Okay? If we can do that from both sides, if we can do something where we get different tangent lines, the tangent doesn't exist. We say that the derivative just doesn't exist at that point. Right? So the first place, we mentioned this on Friday, the first place a derivative might fail to exist is at a corner. The most obvious example of a function that has a corner is the absolute value function. Right? The absolute value function is just a v. So at x equals 0, the derivative would fail to exist. Now we can say the derivative exists everywhere else. I could say that the derivative exists from negative infinity up to 0, not including 0, and then from 0 to infinity, again, not including 0. But at this single point, we cannot calculate a derivative. So another way of thinking about why that would be true would be to actually graph the derivative. So so this is my f. If I wanted to graph my f prime, what would this look like? All right, so what is the slope of this piece right here? -1, right? The slope this is just a line, right? So the slope everywhere here is -1. So on my derivative graph, it's just going to be that value of -1 everywhere. And we said we don't know what the slope is here. We can't define that. So this would be an open dot, right? Now what's the slope from 0 to infinity? +1. Right? So this is what the graph of the derivative would look like. So it's much easier to see then on the graph of the derivative why this point isn't defined. Right? We've got a big jump discontinuity here. So at 0, the derivative does not exist. Right? You okay with that idea? All right, so the next one, we talked about this as well, and this one is really similar to a corner. A cusp is another place where the derivative would fail to exist. And it's for the same reason. Right? If we think about choosing that point at 0 and getting closer and closer to that point, right? Drawing my tangent line from this side, well, and if I do the same thing over here, getting closer and closer, I try to draw my tangent line over here, they're going to be very, very different tangent lines. Right? And this is just kind of an extreme case of a corner. Very, very similar idea to a corner, but it is a little bit different. But same reasoning why the derivative would fail to exist at that point. Right? So I guess just give people a second to sketch that if they want. All right, and then x to the 2/3 power is an example of a function that has a cusp. All right, so the third way that we talked about for a derivative to fail to exist would be a vertical tangent line. Okay, a vertical tangent line. So right here again, at x = 0, if I were to sketch my tangent line, it's going to be a completely vertical tangent line. And the reason we say that this doesn't exist, even though we can draw a tangent line at that point, what's the slope of a completely vertical line? Undefined, right? So that's why we say that the derivative does not exist at this point. Right? The slope is undefined or infinity. And the most obvious example of a function where this occurs is the cube root of x. All right. Now, the final way, okay, there are only 4. The final way that a derivative would fail to exist is at a discontinuity. Okay? Any place where a function is discontinuous, the derivative would fail to exist. Right? And again, it's for the same reason. If I were to try to draw a tangent line at this point, well, I could draw it here, right? But I could also draw it there, or there, or there, or there. Right? I could draw this tangent line at an infinite number of places. Same here, right? At this other point, I could draw the tangent line at an infinite number of places. So the derivative would not exist at that point. Right? Questions on the 4 possibilities of the 4 places places that a derivative would not exist. So a corner, a cusp, a vertical tangent, or a discontinuity. Alright. I'm gonna skip this one for now. Alright, so most of the time, right, functions that we look at are going to be differentiable everywhere. Right? Most functions that we look at aren't going to have corners, cusps, vertical tangents, or discontinuities. Most of them are just nice, smooth, continuous curves. Now, the smooth part is the key. Right? Smooth basically just means there are no corners or cusps. Right? There's no jagged edges. So, if a curve is unbroken and smooth, that implies local linearity, and that's also the idea that we were talking about on Friday. Right? Local linearity just means if I zoom in really, really close at a certain value, a function will look like it's linear, and this gives us a good example of that. So if we take this function, right, it's got a whole bunch of loops and curves. But if I zoom in on a really small spot, right, so this is saying I'm zooming in on the 1.7 to 2.3 area. So I'm just zooming in on this piece right here. If I zoom in and get really, really close to it, it looks like it's a straight line. That's going to be the case anywhere if I zoom in on a continuous, smooth curve, which is why what we did on Friday when we estimated points on a curve using a tangent line, right? So this is like, I sketched out my tangent line to this point. And we said, well, if we can use that to estimate values that are really, really close, right? So if I found my equation of this tangent line, I was able to estimate a point really close on the curve because the tangent line is approximately the curve when I'm talking about values really, really close to that point of tangents. This would not be a good estimate, though, if I were to extend this out and say, well, I'm going to estimate the curve here at 2 using my tangent line. That's really far away, right? But for points that are really, really close to my point of tangency, the tangent line itself is good at approximating the value of the curve. Right? Questions on that idea? All right, we're not going to worry about that calculator just yet. So this is kind of the last idea for today, and then we're going to have pretty much all of class to work on the homework. All right. Differentiability implies continuity. Okay, so we said that one of the ways that a derivative might fail to exist was if it's discontinuous. Well, therefore, if our function is differentiable, then it must be continuous. Okay, and that's kind of a key important idea as we continue through looking at derivatives. Right? If a function is differentiable, then it must be continuous. It doesn't necessarily work the other way around. Right? If a function is continuous, it doesn't have to be differentiable. Right? There could be a corner or a cusp or a vertical tangent. At all of those things, the function would still be continuous. So it wouldn't be differentiable. But if the function is differentiable, then we know for sure that it has to be continuous. Right? So, any questions on any of this stuff? All right.